what I'm going to call the beginning of real physics for the year. What we did in chapter 1 was science, right? Science, the concept of estimations, dimensional analysis, you did in chemistry already. So this is the first real physics we're going to start for the year. And even in this section, or the first 3 sections, you'll notice, when we look ahead, that a lot of this is also part of what you learned in freshman year, in your Algebra 2 or for all of you, Algebra 2 honors course, with distance rate problems. You'll see a lot of similarities to distance rate problems in this section. Okay? So we're going to do 4 main things here. We're going to describe motion in terms of 3 things. We'll talk about a frame of reference. We'll talk about displacement, time, and velocity. 4 things. Calculate the displacement of things in a time interval given. And again, that's got to be at a known velocity. We'll construct and interpret graphs, something we kind of looked at already from the lab. And then we're going to talk about average and instantaneous velocity. So let's jump right in. So the first term we're going to look at today is called reference frame or frame of reference. Reference frame or frame of reference. The idea here is that our current location, placement in time and space matters. It matters a lot. Like right now, what would you say my velocity is? Okay, and that's with respect to what surface? The floor. Is that reasonable to say? Okay. Now, with respect to the universe, what could you say my velocity would be? Anybody know the speed at which the Earth rotates? That's what's that doing. Right, the Earth is rotating, right? So with respect to the universe, I'm moving right now in circular motion with what we're going to call later on tangential velocity. So right now my speed is around 23,000 miles per hour actually, with respect to the universe. But the Earth is sucking me toward its center with gravity, so I'm not getting launched off the surface, which I would if the Earth weren't pulling me toward the center. So my frame of reference matters. A simple example, that one is probably a little more difficult to perceive because we can't really perceive outside the universe unless we're astronauts in space. The easier one to think about is motion on a moving object already. When you get on the subway, when you're on the subway and you're standing there, right? And you look out the subway, and there's a subway car next to you. And it looks like the people next to you are just kind of cruising along. It doesn't look like they're moving. It doesn't look like you're moving if you're both moving at the same speed. But if they're moving a little faster than you, when you look out that window, you see them going by like this, right? You ever wave at people like that? You ever do that? You should do it sometime. We're never going to see them again. Do it next time. It's kind of weird, but just wave. Now, or you can start tossing an object up and down like a physics person, like, what's happening? The object's moving with me. It's your inertial reference frame, whatever. So when you're moving though in the train, if you were to start to walk in the train, your actual velocity would really be the sum of your velocity and the train's velocity. Think about that for a second. If the velocity is traveling, if the velocity of the train, and the train is traveling at 20 miles an hour, and you decide you're going to get up and just sprint to the front of the train, something happens, somebody's smelling in the back of the train you got to go away from. So you sprint toward the front of the train, you get to the front of the train. As you're moving, your velocity is 30 miles an hour, plus, let's say you're sprinting at 15 miles an hour, you're a pretty good sprinter. So your velocity really is 45 miles an hour with respect to the train tracks or the platform that you're passing. Say you're passing, 51st Street on the express train going downtown. Your velocity is the sum of those 2 velocities because now you're comparing your velocity to the platform. Well, you got the train and you moving together. What if the train is moving 30 miles an hour this way, but you're moving 5 miles an hour this way? Then what does it feel like you're moving actually with respect to the nearby surroundings? Be 25. Because again, you're moving the train's moving 30, but you're going against the motion of the train at 5. So if somebody were outside the train watching you, they would see, you're moving this way, walking, but your body would still be going that way compared to where they are. Because the train's velocity is greater than yours backward. If your velocity could technically be greater than the train, you'd be moving backwards actually. But it's not going to happen anytime soon. Yeah?
So if you're on a treadmill, is your velocity 0?
Say again?
If you're on a treadmill, sprinting.
It depends on what you're relative to. Relative to the treadmill surface itself, you have velocity. Relative to the ground next to you, you have 0 velocity. So your frame of reference is what changes there. if I'm considering the treadmill to be the frame of reference, then I'm technically moving with respect to the conveyor belt itself. I have a velocity of 10 miles an hour. But compared to the floor next to me, have I moved at all? No. I'm literally in the same spot compared to your little brother or sister watching on the treadmill. You haven't physically moved. So it's always with respect to that matters. Okay, your velocity with respect to is what matters. Okay, let's take a look at this next terminology here, displacement. So the concept of displacement is very much like what you did in the lab on the roof on Thursday. And the idea here is that your displacement is a change in your position. Your position. Now, we are going to call our current position in all terms of physics, we're simply going to call that x. So maybe put an arrow here and label that current position. x0 is going to be called our starting position. Another phrase for this, which is widely used in college, so get used to it. x0, another phrase is x0. N-A-U-G-H-T. x0. Another phrase meaning zero, not, nothing, zero. So your current position is denoted by x. Your initial position is denoted by x0 or x0. And your actual displacement is the change that occurs. In Greek, change is symbolized by what symbol? Delta. So we see delta x, or the change in your position, that's your displacement. This symbol means displacement, delta x. Okay, and displacement by definition is the change in your position. Now, something to write down. This is one of our notes that is not on here, but you should note to yourself. Displacement is a vector quantity. We're not going to get into vectors too much yet. We will in the next chapter, in chapter 3. But I want to mention this now. A vector quantity has a magnitude. Another word for magnitude is value, if you want to put parentheses. And a direction. Again, a vector quantity has a magnitude and a direction. Another word for magnitude is value. Value. Quantity. Those are fine. So, what do I mean by that? If displacement is a vector quantity, by moving to the right, what kind of displacement would you consider me having? Good. But Isabella, if I move to the left, what kind of displacement do I have? Negative. So the vector quantity here simply indicates that direction matters. So what are we going to say in general? God bless you. We are going to use our xy axis, our traditional Cartesian coordinate system, as our denotation. So on the Cartesian coordinate system, this way is positive, this way is negative. Agreed? I'm making an xy axis right now. And then this is positive and this is negative. We've always accepted that. We could change it today. And you know what? When I was in high school, my AP physics teacher, and when I was a senior, the second time I took physics, actually for the first 2 weeks of school, just to mess with us, to prove a point that it doesn't matter what direction you choose, as long as you're consistent, he made everything up negative and down positive, and left positive and right negative. For the entire first week or 2 weeks of school, just to change our mind thought, or our mindset, or our thought process. I'm not going to do that in the first week because we haven't adopted a thought process yet. But maybe next year, if you have me for AP Physics, I might do something like that, where it's going to think differently each time. Okay, but we are going to adopt the notion that right is positive, left is negative, up is positive, down is negative. Okay, if you have a question, just stop me. I'm not always going to say any questions because I want to continue the class and keep moving along. So let's look at our first example, a very simple one. We can talk through this together. No need to do it individually, it's not a lot of math. A space shuttle takes off from Florida, encircles the Earth several times, finally lands in California. While the shuttle is in flight, a photographer flies from Florida to California to take pictures of the astronauts when they step off the shuttle. Who undergoes the larger displacement? Who undergoes the larger displacement? So by who we mean the astronauts or the photographer in this case, right? The astronauts or the photographer. Mr. Genesi, what are you thinking?
Well, I would think that the astronauts would, because they're going around the Earth multiple times.
And landing in California?
Yeah.
Whereas the photographer is doing what?
Just going from Florida.
Okay. I like the idea and the logic behind what you're thinking. Want to help me out?
Would it be the same?
It might be the same though. That might be an idea to think about. George, why might be the same?
Because given it's just your current location and the starting location, those are the same for both of them.
So that's right. What did Jack refer to then? Help Jack out there. What was he referring to when he said one was much larger than the other? Was it displacement? Distance traveled. So that's a really good point, and it's okay that you made that thought in the first time through. But now we write a note down. Displacement in this problem is the same. They both start in Florida. They both end in California. But the distance traveled in this problem is not the same. Sometimes they will be the same, and we'll discuss that in a moment. Again, the distance traveled for these two scenarios, or these two movers, the astronaut and the photographer, these two objects in motion, the distance traveled are not the same. Are not the same. So the astronauts clearly travel a much longer distance because they circumnavigate the Earth several times, okay, before landing in California. Now, the idea of distance and displacement is really, really important, and we're going to keep going with this for the next example, okay? So let's go right into the next example. So example 1, you would consider on one of my tests a theoretical example or a short answer. On my test, to give you a format, because we're talking about these problems, I have multiple choice, I have what I call short answer, and what I call mathematical. This would be categorized as a short answer. If there were choices, it would be a multiple choice, obviously. Multiple choice can be math-based or theory-based. But your short answer are mainly going to be theory, and your longer answer are your mathematical problems. So this would be a short answer. The next one would be a mathematical one. It looks lengthy, it's just really wordy. Okay, it's just really wordy. It's not a tough problem. Can I get a reader to read it nice and loud for us? Go ahead, Christina.
Your office, the deli, the subway station, and the nearest electronics store are located at the following positions, respectively. X1, 20 meters, X2 equals 240 meters, X3 equals 140 meters, X4 equals 280 meters. You arrive at work in the morning, and from that point on, you do the following. Leave the office and go to the electronics store for a new pair of headphones at
Oh, Nora, sorry, title. Go ahead.
Then go to lunch at the deli. Next, you head back to the electronics store for an adapter to connect your headphones to your phone. And finally, walk to the subway station to take the train downtown for a meeting. At this moment, waiting at the subway station, what are the values of your distance traveled and displacement?
So what might be useful, thank you, Christina, for a problem like this to start? Just to start it, what do you think might be useful?
Draw a photo.
A diagram would be really nice for here, really useful here, or very nice here. The reason being is it's very wordy. You notice that? A problem like this? On a physics SAT subject test or AP exam, at times wordy problems can get confusing. So a diagram is very, very useful. Caroline?
I have a question just about like the structures of problems.
Yeah.
So it asks, it says you arrive at work in the morning. Did you get off the subway?
Well, read what it says. You arrive at work in the morning, and from that point you do the following. Leave the office. So where must you start the problem?
The office.
At the office. Yeah, that's okay. And it's purposely written this way because you want to, in physics, recognize where a problem begins and ends. Let's write that down, actually. It's really important to denote when the problem begins and ends. We're going to have problems this year that are really complex, and we're going to have to break them into 4 or 5 parts. So I might call the first part like part A, where like the person leaves the office and goes somewhere else and does something. Then part B, maybe they leave the store and go somewhere else, and that involves friction, so I have to make it a new part of the problem. So throughout the year, we're going to what's called truncate or break up a problem into important parts. So it's really important to recognize where it begins. So in this problem, you begin at the office. So a diagram would be useful. You can start drawing a diagram if you want, but keep in mind where your locations are respectively. Okay, the office is at 20, the deli is at 240, the subway is at 140, and the electronics store is at 280. Respectively means in the order it was given in the problem is the order of the locations x1 through 4.
Do the distances mean like from your home?
So again, it just says, at this moment, from waiting at the subway, what are the values of the distance traveled and the displacement? So from the office, doing all that stuff, ending at the subway, what was your total distance traveled and what was your displacement? So from the office,
But do they mean like the 20 meters, does that mean 20 meters from your home, or does that mean like?
it means somewhere on the x-axis. Let me draw a diagram to help
Oh,
us.
okay, so this is subtracting.
Yeah, so this problem, again, whenever you're given x values as positions, I want you to start thinking about a number line. Right now, we're only doing one-dimensional motion, so everything's going to be only along the x-axis or along the y-axis. Later in chapter 3, we're going to look at projectiles that are launched at angles, and they move both in the x and the y direction. Here, I'm thinking about this as flat land. So I've got the office right here at 20. At 240, I've got the deli. At 280, I've got the electronics store. And then here at 140, I've got the subway. So that would be my diagram for a problem like this. Do I care about numbering every other number? No, this is not 6th grade math where you number everything on a number line. Don't waste time. On physics exams, you're going to notice, because it's a critical thinking exam, that you will lose time thinking about an answer. Don't lose time adding extra stuff along the way. So I only denoted those 4 locations. I then read through the problem. As I read through it, let's denote with colors. So the first part says, you leave the office, and you go to the electronics store. So here's our first denotion right there. That's our first path. Okay, leaving the office and going to the electronics store. The second one in blue, you then go to lunch at the deli. Well, you're at the electronics store. You can't just teleport. So you're starting at the electronics store now, and you're going to the deli. Then it says, next you head back to the electronics store because you forgot that adapter on that stupid new iPhone that doesn't have an auxiliary port for some crazy reason. Does the new one have it or no? Anyone know? The iPhone 11 came out like 2 days ago, apparently.
Yeah.
Did they put the headphone jack back or no?
Probably.
That's stupid as hell. So you go from the deli back to the electronics store. Okay, so now you're back in the electronics store getting those headphones or that adapter you hate to pay for. And then finally you walk to the subway station to take a train downtown. And where are you walking from? Well, you're walking from the electronics store. You can't teleport. So you've never gone back to the office. You're playing hooky this day pretty much, right? You go to the subway, and you end up at the subway, and you get on the subway to go downtown. But you know what? When does the problem end? Does it end when you're downtown? According to the wording, when does the problem end? When does it end? When does it end? At the subway station. So let's denote our starting and final position then. This is x0. This is x. Does that make sense what I'm saying? From beginning to end. So what is my overall displacement, people? This is the easier part of the problem, obviously. What's my overall displacement in this problem? What would I get as a value here? I'm seeing the same hands all the time. What am I getting? Julie, go ahead.
Positive 120.
Positive 120. Very good. And again, I get that because I take my final or current position and subtract my initial position. 140 minus 20 is 120. So my displacement, x, is going to be, again, 140 minus 20, which equals 120 in the units of meters. So there's my displacement for this problem. But the other part I got to get still is the distance traveled. Distance traveled. So it's very easy to do it by just adding numbers together right now. I'm going to write down some symbols that would help you going forward and also next year when you're in AP Physics and Calculus. So here's how I would calculate the distance. I would say first that the distance, I'm going to use the other side of the screen over here, that the distance is equal to the following. It's equal to the sum of all of my displacements from, and this is the hard part, it's hard to use the symbols because I'm not using the subscripts the way you would in calc, but from, let's say, part 1 to part 4. And the symbols look weird right now. Don't worry, because you're going to learn these in pre-calculus. I'm trying to give you guys like little head starts. This is a summation, and because there are 4 parts to this problem, I'm going to put a little I subscript on the outside here, indicating that I'm going to sum together this number 4 times, once for each part. Why am I putting absolute value? Why am I putting absolute value?
If you have negative motion, then it's subtracting, but really you're moving further, so it should be more.
See what she's saying? Like if I walk this way 10 meters and then come back 3 meters, what's my distance traveled? 13 meters. 10 plus the 3 back. But my displacement would be 10 minus or plus a negative 3 if I did displacement. Is that clear? Displacement direction matters. So for distance, my values I need to sum together are these vectors drawn in the 4 colors. But if I look at the blue or the yellow one, it looks like those vectors are negatives, right? But really, I need to recognize that if I'm looking at distance, I need to take the absolute value. So really, my distance traveled here, again, is going to be the sum of these 4 paths taken. Oops, I don't need another plus sign. So I'm going to fill in those blanks now. But again, the distance is the sum, that's this symbol here, summation. I equals 1 to 4 means from the first motion to the 4th motion. That's why the I is that little subscript down here, indicating that it's going to change how many times you add this together. Well, let's take a look at my first motion. My first motion would be 280 minus 20. And where is that coming from? Where's the 280 minus 20 coming from in the first bracket there, Isabella?
Well, it's from the office electronics work, but like you have to know that you have to minus 20 because the office starts at 20. You can just leave it at 280.
Yeah, so this is like my final position at the end of part 1, right? This is how many parts again? There are 4 parts to this problem. That's my final position, that's my initial. So final minus initial gives me delta. So 280 minus 20 gives me the overall displacement, which is 260. I put absolute value, so I guarantee that's a positive number. How about my second motion along the blue line, Seb? Technically, thank you, very good. It's technically 240 minus 280, but it's inside the absolute value. Again, it's the second segment. My final position along the second segment is right here, which is 240. My initial position along the second segment is at 280. So it's final minus initial. So 240 minus 280. But because it's distance traveled, I want the magnitude of that, not the direction. I want only the value. And the value is indeed 40. Okay? The third vector along the green path, Jackie?
280 minus 240.
Yeah. 280 minus 240. This is the opposite of that one. Very good. 280 minus 240. Because my initial is 240, my final is 280. Final minus initial, 280 minus 240. And last but not least,
140 minus 280.
we have 140 minus 280. 140 minus 280. And why is it 140 minus 280 again? Or 280 minus 140? How come, Justin? So your hand up also?
Because 140 is the final position.
Good. 140 is the final position, and it's always final minus initial. So what we end up getting here is going to be what? 260, 40, 40, 140, 4 and change. What do we got? 480, I think? Yeah. 480 meters. So pretty much that day you walked about a quarter of a mile. Quarter of a mile. Good numbers to know, by the way. Maybe jot that one down. Anybody know miles in meters? 1,600 meters. Anybody that runs track cross country probably knows that one. The 1,600 meter competition. Or is it a 1,500 meter in track, or what is the track?
They usually have 15.
It is a 1,500, you see? Okay.
16, and then for the girls it's 14.
Is that really what it is? So the boys race a mile, while the girls race 1,500 meters.
I know, it's weird.
It's weird. It's not like they're competing against each other or anything.
It's just they make the girls run last.
It's
It's
stupid.
like that for a bunch of other reasons.
Really?
It's like tennis, how they have women play like 3 sets and men play like 5 or something.
Is that right?
Or like the boys.
It's kind of messed up.
The boys also have the 32.
You should start a platform about that. That's pretty messed up. Yeah. Let's move on to the next problem, or the next topic. So, average velocity. Pretty much what we did with the motion detector lab the other day. Average velocity. Let's talk about this. So, average velocity, by definition, is the displacement of an object over a given time interval. And the formula is written just that way. Anybody ever seen the line over a variable before? A line over a variable? Maybe, maybe not. If you ever did anything with statistics, maybe in middle school, I was thinking of it.
I had a calculator when finding like the mean, it's X.
Yeah, very good. The mean. The mean in statistics, and mean means average. Okay? So when you see a little bar over something, it means average. If you didn't know that, you should probably write it down. Okay? Because that's going to happen throughout the year. So a little bar over something means average. You see it in statistics also if you take AP Stats next year. Now, with that said, let's take a look at the first example, because there's really not much more I can give you on this besides the formula for now. By the way, what is in bold on the right there? I didn't discuss it in the last formula. What's in bold on the right? What's always going to be there pretty much, George?
The units.
The units, okay? When I put something in bold in brackets, I'm referring to the units in that problem. So the last formula was delta x, and m was in brackets standing for meters, okay, for meters, not for miles, obviously. Let's look at example 3. During a drag race, and a drag race, by the way, is where there's no turns. It's a straightaway. So your book refers to drag races a lot. You need to know that it's only one dimension. You're not turning the car ever in a drag race. Fast and Furious, have you seen the originals? The drag race novels? So during a drag race, no turns on level ground, Jamie drives her go-kart, go-kart drag race, her go-kart with an average velocity of 6 meters per second. How fast is 6 meters per second? It's 6 times faster than this. This is one, remember I talked about 1 meter per second? 1 meter per second are big steps. So a big step is about 1 meter per second. So 6 times faster than that. So you have a number sense of what you're qualitatively looking at. What is her go-kart's displacement in meters after 2 minutes and 17 seconds have elapsed? What is her go-kart's displacement? So this is what I was talking about for the problem set format. Here's how I want you to do format all year. Yeah, this is an easy problem. I know it is. A lot of you are like, I can figure it out in my head problem. But the format I want you to use all year is as follows. Start by listing the givens. So we're going to do this with the right format together today. And then going forward, you're going to have to pick and choose when you want to adjust your format accordingly. So what is given in this problem? What values are given?
Time and velocity.
Very good. And it's average velocity in this. Oh, actually, does it say? Yeah, average velocity, which is different than just saying velocity. Let's keep that in mind. So those values are given. Time is 2 minutes, 17 seconds, and the average velocity is 6 meters per second. East. What are you thinking? East.
Going to the right.
Good, which means it is?
East.
Therefore, the sign on the velocity is? Positive. Very good. If I said west? Negative. If I say north?
Positive.
South?
Negative.
Okay? Know those directions, please. Okay. Now, those are the two values I have. Can I go right into my formula? Can I use my formula v bar equals x over t right away to get x, or delta x rather? Can I do it right away, Maura?
No, because it's the unit is 60 per second, and you have unit 10 seconds.
Very good. The units don't agree. If your velocity is in kilometers per hour, then your time has to be in hours. If your velocity is in angstroms per minute, then your time has to be in minutes. Our velocity is meters per second. So our time lapse needs to be in seconds only. So let's convert. 2 minutes, how many seconds is that? This is one of those times where you're not going to write out your word for converting. You could, but if you don't know that 2 minutes is how many seconds, then you probably don't belong in this class, to be honest. I'm not trying to be mean, I'm being honest though. You should know that 60 seconds are a minute, and if it's 2 minutes, it's 120 seconds. So this value is 120 plus 17 seconds, or simply 137 seconds. So right away, convert your units if you have to. Again, when necessary, show the conversion. When it's simple, do it in your head or in your calculator. Okay? Now, at this point, we can go ahead and start our formula. Well, let's look at what's desired. I call this the desired variable, or the variable that you're seeking. Whatever you want to call it, you can call it. But the desired variable is the go-kart's displacement. What variable is that? More specifically, not just x? Delta x. Delta x. Because x would be the position at a given moment. So we go ahead and look at our formula next. What formula involves these three variables? This is how we're going to approach all of physics this year, by the way. You're going to have, if you recognize already on your formula sheet, a ton of formulas, right? You notice that? There's a lot of them on there. Well, you need to look at the variables given and say to yourself, what formula involves these three variables? Or at least these three variables. And what's the only formula we know, Jack?
Speed equals distance divided by time.
No, what's the formula we just used? We're looking for displacement, and we talked about velocity, so use different words, Jack.
Oh, that's what you, okay.
Yeah.
Change in the displacement one?
Yep.
So x minus.
No, sorry. Help me out. You're just using the wrong terminology, Vin.
Average velocity equals delta x over delta t.
Good. So, in a moment, Jack, we're going to talk about speed and distance and time being very different than velocity. So I don't want to confuse anyone and use the wrong terminology here. So we are not referring to speed and distance in this problem at all. We're going to see that in a moment when we get to those problems. So right now we're referring to average velocity, and we're referring to what we call displacement, as the words were shown in the question. So we need to figure out the displacement. So this is what I mean by generic solution now. A generic solution in physics involves no numbers. It means solve for the variable of interest. What's the variable of interest in this problem again? What is it, Seb? Delta x. So Caroline, if I solve for delta x, what do I get in the equation?
So you're gonna have delta t times the average variable equals
Average velocity. Very good. Very good. It's all right. Average velocity times delta x, times delta t, is our delta x. How do I get that? I just solved this equation. Think of delta t as a number. If you were taking your variable of interest, for those that are struggling with this is why you had you do your summer packet, by the way. If I think of this problem as this, think of it like this. And these are not the right numbers. These are not the numbers for this problem at all. Okay, that's how you would approach this kind of a problem. How would you solve this for delta x? Whenever you're stuck, put numbers in for the variables that are not of interest in your mind. How would you do it? You would multiply by 5, and this would become 5 times 10. So you're going to multiply out by delta t. So it's delta t times v bar. I write it as v bar times delta t. Okay? And now, your final step in all problems is to plug in the actual givens. You might be saying right now, Mr. Howell, you're freaking nuts. I could do this faster if I plug in numbers earlier. I don't have to worry about this generic solution crap that you're telling me about. Trust me for now, please. As we get to more difficult problems, this methodology will become very useful and powerful because I can vary things very slightly and I can change my result.
Should we show how we found delta t? Because we were going to start at 0, right? I'm still
I like you, Vin. Very good. So Vin's right. Technically, I should write 137 minus 0 for delta t. Very good, Vin. Because what time did this problem start at? If we don't give a time to start at, we assume the start at time equals 0. Very good, Vin. Some problems throughout the year will denote that a problem starts 5 seconds in, where you start calculating your data or recording data 5 seconds in. So you have a coordinate of t equals 5 and a displacement or position of 10, and a t equals 7 and a position of 12. And then your delta t you have to subtract. So a very good point, Vin. It should be 137 minus 0. Minus 0. Now our answer for delta x is not x or x0, it is delta x. The answer we get here, and that gives us 822. And my answer is definitely positive because my velocity was positive. So I don't know if I started at 0 and ended at 822, or started at 100 and ended at 922. Or started at 200 and ended at 1022. Does everybody follow what I'm getting at by saying this multiple times? This is only my net displacement. It is not my starting and ending point. So again, this problem, although written as if it's a starting line because it's a drag race, I could think of this problem as the following. I could think of this problem as starting at 0 and ending at 8 not drawn to scale, figure not drawn to scale, and ending at 822. I could draw this problem as starting at 100 and ending at 922. I could draw this figure as starting at 200 and ending at 1022. You follow what I mean? All I know is that my displacement was 822, 822, 822. But it could be any of those three vectors in motion. I could start at 0, I could start at 100, I could start at 7, I could start at 12. I could start at negative 2,000 and then add 822 to that, and we'll see where I end up. So again, delta x is your displacement. It doesn't tell us where you start and end. It just tells us how much you've covered from beginning to end. From beginning to end. All right. Can we go to example 4? Yeah, let's keep moving. So example 4 says the following two students walk in the same direction along the straight path at constant velocities. This whole section is going to be these kind of problems. One of them is at 1.5 meters per second. The other is at 2 meters per second. Assuming they start at the same point at the same time, how much sooner does the fast student arrive at a destination 500 meters away? So, we can do this problem two ways. Can anybody foresee the two ways we can do it already? There are 2 ways to do this problem. Give me one of them.
The first way is using just regular math.
First way, just using regular math. What do you mean by that, Regina?
Like, so you would take the distance and divide by the velocity.
Yeah, so you could do it twice. You could do it for the slower person. You could do it for the faster person. You'll get 2 times as answers, right? And then what are you going to do with those answers? Subtract them to see how much quicker one got than the other. That works. That definitely works. Want to stick with that for now? Let's start with that. Let's see if anybody picks up another idea. So let's say object or student or person number 1 is moving with a velocity on average of 1.5 meters per second. The second person's average velocity is 2 meters per second. They both move the same distance because they're running the same race or walking the same race. I don't know if I'm starting at 0 and ending at 500, but I know delta x is surely 500. Okay, I could be going from, again, 0 to 500, or 100 to 600, or 200 to 700. But I know that delta x is that number. So in both problems, I'm searching for delta t. Notice I don't write the words given and desired variable anymore. So I wrote it on the first example. I'm not going to waste time writing those words every time, but the structure is in my head. It's literally ingrained from taking physics in high school, studying engineering, teaching physics for the last 11 years. So it's ingrained. It's not going to be ingrained in your head today, but hopefully soon it will be ingrained that you always start with given, desired, then formula. So here's my given, here's my desired. And I should denote my desired with different subscripts because they're going to be different. So my desired should have subscripts. Delta T1, delta T2. Why is delta X not given with a 1 and a 2? Why is it not given? Because they're the same. If I tell you the mass of one object is the same as the mass of the other object, you can call them both M instead of calling them M1 and M2. It's when things are different that we denote with the subscript to indicate the differences. The formula being, again, V bar equals delta X over delta T. V bar equals delta X over delta T. My solution in terms of variables for delta T, this is one that happens all the time, by the way. This one shows up all the time. How did I get that generic solution so quickly? What operations did I perform? How did I get those so quickly? What's the quick way of getting delta T by itself? What am I doing with this formula here?
Just dividing it and you're switching places of delta velocity and delta T.
Very good. Recognize here. Guys, this is just division. So really you're going to eventually divide by V, but you're going to multiply by T. So what are you just doing with these two variables? You're just switching. Whenever you have a formula that's triangular in nature, where you have a numerator and denominator, you can always switch diagonally. It's a proportion. When you were in like 4th grade, you learned this thing that you were like, I'm never going to use this. And it stated the product of the means equals the product of the extremes. And it's like a really old thing. And here's what it means. It simply means that I can cross multiply and set them equal. But I can also cross change my positions. So whenever you get a triangular formula and you're looking for something that's in the denominator, simply move it up here and switch it with what's up here. So those two switched. Okay, so I multiply by t and divide by v. So what do we get in these problems? We have 500 over 1.5, and this is in meters, and this is in meters per second. And the second one is 500 over 2. 500 over 2 is 250, that's easy, and that's in seconds. And 500 over 1.5, what am I going to get? 333.3. And that's going to be repeating. Are those my answers, though? They're not my final answers. What's my final answer in this problem?
The difference between the two.
The difference between the two. Okay, delta T1 minus delta T2 is going to be 83 seconds. 83.3 seconds ahead. 83.3 seconds ahead. All right, I'm going to leave it like that for now. I'm not going to jump into that and get ahead because I don't want to confuse anyone or get ahead of myself. So a problem like this has two parts to it. Those parts are coupled. When I say coupled, it means they're used together. A problem where the parts are uncoupled is they're not related to each other. It's like part A, part B, part C that don't affect each other at all. But these two parts of the problem affect our final answer. So we would say that they are coupled. Coupled. A good word you're going to use a lot if you study engineering. Yeah.
Would the other way be to use like 0.5 meters per second as the difference, as the average velocity of the difference in it? So you don't need to do it once.
What would you get if you did that?
Probably the same answer. Oh no, you would get the difference right away.
You have a right idea. So Morrow's talking about relative velocities of the two objects to see a gap changing. It's more applicable for problems where we're trying to figure out, like, how long will it take to catch up to the other object? Or how long were they closing the gap when two trains are heading toward each other? That's when the difference in velocities is more useful. Because here, the difference in velocities would be 0.5, right? And then where would I utilize that, Morrow? How would I end up getting 83.3? Think about it as we're doing the next part of the problem. Just think about it mentally, and I want you to recognize that it probably wouldn't be as applicable here as it would to a later problem. That's why I stopped to not say that, okay? But good idea. I like the idea. Velocity versus speed. Let's get into this. So velocity we already talked about, right? Velocity is delta x over delta t. Speed is going to be distance over delta t. Average speed is your distance traveled over delta t. So d will denote distance and delta x will denote displacement. Well, you can see that this is analogous to the velocity formula that we spoke about a moment ago, again, which is this. So depending on the problem, we are going to use a different formula. So when I'm asking about speed for a problem, we need to use the overall distance traveled over time. So let's give a conceptual question. You leave New York today and you go to drive somewhere. I don't know, you're visiting a college up in Boston. How many people have been to Boston at some point in their life, or the Boston area? Okay. So you know if you've driven there, can you drive directly to Boston? Like straight line directly to Boston? Obviously not. From New York City at least, or from Long Island. So you have two options. You go to Long Island, you get on the ferry, take the ferry across with your car. That's a pretty cool ferry I've never done before with a car. You get off with your car, and you drive to Boston. Or you drive from the city, kind of around, into Boston. Right? So when I ask you the following, tell me how fast you were moving on average during the trip. Tell me how fast you were moving on average during the trip. When I ask that kind of a question, physically, am I asking about your average speed or your average velocity? Which of those, that's an X by the way, sorry. Which of those do you think I'm referring to when I ask you about your average speed or your average velocity? Which am I referring to here? I'm going to say how fast you're moving. Vinny, what do you think?
Speed.
Why do you think it's speed, Vin?
Because you're not going straight for because using displacement when you're going straight to it, that's all.
Yeah, you're not physically going straight there. So you can't use your displacement really. That would be giving your average velocity, which takes into account the curvature. So let's draw this path. So here's New York. Let's say the path you take is up I-95, then around. You have to go a little bit down, then come back up into Boston, and then you end up at South Station. From there to there, the black line drawn is your distance traveled, where the red line drawn is your displacement. So when you're asked to find your average speed in the problem, it matters how far you physically go on the curved path. So when you're trying to find how fast you're going on a trip, you're always regarding or referring to your average speed, unless asked elsewise. Unless the problem directly says, what is your average velocity? And then you would use this length of delta x divided by your time period. But if a problem simply says, at what average rate were you driving? Like what average rate would your speedometer show? That's the average speed you found using distance, not displacement. I saw a hand pop up at some point when I was talking. We good? Okay. Let's look at an example to see this. So a book is moving or is moved on a table around the edges. The table's dimensions are given. If the book ends up at its initial position, what's the displacement? If it completes its motion in a certain time, what is the average velocity? And then finally, what is the average speed? So this is a very easy problem, and the reason I say it's easy is because there's not actually much math needed here. So what is the average what is the overall displacement of this textbook if it again ends up at its initial position? What do you think, Nick?
No displacement.
No displacement, very good. Okay, and again, why is that? Because it's final minus initial position. And if I need a diagram, here's my diagram. My initial position, starting in the bottom left corner, equals my final position, x. So when I use my formula for delta x, which is x minus x0, if those values are the same, it must equal 0. It must equal 0. Now, the path taken, though, is shown with the dotted lines. And if I sum together those four values, what am I getting instead? If I sum together those four dotted lines, I'm getting not the displacement, but the distance. And I'm going to do this twice, right? So I'm going to put times 2. Can everybody bear with me there? I'm going to have to show it 4 times, please. 175, 2.25, 175, 2.25. So I'm doing the width and the length twice, so I'm putting a 2 on the outside. So my total distance traveled in this problem is 8 meters. So I've got my displacement, I've got my distance. I'm now asked to find the average velocity. And then I'm asked to find the average speed. So clearly they're going to be different if I'm asking to find both, right? Or there's a good chance that they have some differentiating characteristic. So my average velocity, if you remember, keep putting delta there. My average velocity is delta x over delta t. But my average speed is going to be my distance over delta t. So my speed is 8 meters over the total 23 seconds, while my velocity is 0 meters over 23 seconds. So although it's not logical to state this, your average velocity is 0. Okay? But it doesn't make sense because you're like, wait, I moved. So how's that possible? So most of the time we talk about things, we're talking about average speed. Average speed, and it's approximately 0.35 meters per second. Okay? Again, the 3 answers that were asked. First were displacement. Second was average velocity. We needed distance to find speed, so I wrote my distance formula down here, and I calculated distance, but I didn't actually ask about it in the question. So those are my 3 answers. So what conclusion can I draw? What conclusion can I draw? Yeah?
That the average velocity is directly affected by the displacement of the object.
Good. While the speed is affected by not the displacement, but the... Good. What else can I draw? Other conclusions. Come on. from a simple example of the conclusions. For any problem, if you take this problem and generalize it. For any problem, if you, what did we do in this? Thank you.
If you end in your starting position, the velocity is zero.
If you end where you started, your displacement and average velocity net out to be 0. Listen carefully. What I'd like to do is the following with graphs of motion. So first, this is, the good part about this part of the notes is that this is kind of a repeat of what you learned in the lab. Okay? When you guys did lab 2, you talked about motion detectors, you discussed the concept of position versus time. And that's really what we're about to get into with this set of graphs of motion. So the first thing we have to recall is that slope is really rate of change. Underline rate of change. That's the most important part here. Slope is a rate of change. Now, depending upon what the y-axis is, that rate of change can have many different meanings. For example, if I were an investor and I were looking at stock prices, on the y-axis is the value of the stock. What's on the x-axis usually? Time. So it's the stock's value as a function of time. It's the amount of dollars per day that the stock increases or decreases by. That's the rate of change of that function. What's another function you could think of that has a rate of change? Not position, time, and velocity, time. What's something else you could think of that you could plot on the y-axis versus something on the x?
Apples per year.
Apples per year. Okay, I like that. So the amount of apples grown in the Northeast region, whatever it would be per year. And we could see if the amount of apples growing is decreasing or increasing. But again, a rate of change, right? And what you'll notice in physics is that many things are functions of time. So a lot of the time is on your horizontal axis. Okay, so get used to time being on this axis. Now, the vertical axis is what will always change. Sometimes the horizontal axis may not be time, and we'll discuss that idea, but for the most part, it will be. Now, if we think about our slope as the change in the vertical coordinate over the change in the horizontal, and I look at a graph of simply position versus time, well, what this tells me is that I'm looking at the change in position over the change in time, if I find the slope of this. And that's just what velocity is defined as. Think back to the beginning of this section. Last week we talked about velocity, and we said average velocity is your change in position over time. And that's what this is saying right here. So we can conclude that for a curve or for something like this, at any moment, the slope is the velocity. The slope is the velocity. So let's look at this first, and then we'll get into a couple simple ones so you can see it. But let's look at this position graph. This means, and this is based on Lab 2, this means that the person or the object starts, well, we should really connect it to the y-axis somewhere, so we know we start at time equals 0. So the person starts at some distance from the motion detector. Let's call this eraser the motion detector. So I'll be that person. I'm starting here at some distance away, maybe a half a meter away. And then my position starts to increase, right, until it gets to here. So then I'm really just moving pretty quickly this way. Then when I get to that peak, what do I do when I get to the peak for a moment there?
You're moving back.
You start to then move back. So what must I do between moving forward and moving back?
Stop.
I stop. So let's put a little dot here at the peak. That means stops. And then I start to move back a little bit, a little slowly, because my steepness is not great. Okay, very low slope. So I move back until I get to here, and then what do I do again? I stop again, and then which way do I turn now? Now I start to turn forward. This represents motion away from the motion detector. So my graph is a low slope, so I'm moving slowly, slowly, faster, 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 faster. And then I slow down again and stop again when I get to the top here. And then again I start to move backwards toward the motion detector, and then eventually it gets flat, so I stop at the end. So what I want you to do is this. Along this curve, pick 5 points. Make 3 of them your max and mins. So let's put a point here, here, and here. That last point was not meant to be a minimum, it's just the end of the graph for now. Then let's pick 2 other arbitrary points. By arbitrary, I mean random. I'm going to choose here, and I'm going to choose over here. Okay? So I'm going to choose those points. And what I want you to recognize is that at those given moments, the slope in that small region differs. And let me show you what I mean. So in the first blue point, or at the first blue point here, the slope at that instant is the line I'm drawing right now. It's that line right there. But then later on at the other blue point, this is what the slope is. And I talked about this word last class. What was the word for that? What was the word? The tangent line. Very good. So last class I brought up the concept of the tangent line, and I said, well, the slope is really the tangent line slope. So here, again, if my position is increasing, I must have positive velocity. But then over here, my position is decreasing, and therefore I would have, in that case, negative velocity. Well, the slope lines up with that. When the slope is positive, we know that our velocity is positive. When the slope is negative, we know that our velocity is negative. V greater than 0 means the velocity is greater than 0, positive. V less than 0, the velocity is less than 0, therefore negative. And again, I'm really getting that from the slope at that moment. Positive slope, positive velocity. Negative slope, negative velocity. What is the slope at the 3 red points, Vin? 0. Vin, you can answer that 2 ways. How did you answer it? What did you use for logic? How did you know it was 0? Yeah, when the tangent line is horizontal, he's absolutely right. When the tangent line is horizontal, that's a slope of 0. That's a slope of 0. How else could you have answered that? How else would you have known that the slope of those 3 instances is definitely 0? What did we say you physically do there, Mauro? You stop. At these moments, you have to turn around. The only way you can stop and turn around is if your velocity is 0 for that instant in time. Okay? This will lead into what we're going to call instantaneous velocity. Okay, instantaneous velocity. Sneeze. Excuse me. Thank you. Let's go to the next slide to take a look at this. Go through a couple cases. So first case. Make sense of this first. By the way, look at your units for velocity. This is an old figure from an old text. And they used to write units with negative exponents instead of fractional. What's the unit for velocity? Meters per second. Yet this says meters times second to the negative 1. It's the same thing, right? A negative exponent means make it move to the bottom, make it positive. So if you want to jot that down, that's really meters per second up there. So it's good to know, because you can see that on like an AP exam when we use negative exponents then. Now, the portion of this that really matters is the fact that we have a stationary object. And what will the position be of a stationary object? What will the position be? It will be the same the whole time. So we see a constant function for position. Now, what's the slope of a horizontal line? Vin told us a minute ago. What's the slope, everybody? 0. So if the slope of this line is 0, then the velocity function must be 0. It's hard to see, but it's actually highlighted right here. Okay? The velocity of this particle must be 0. It's logical. A, because the word stationary. B, because the slope here is equal to 0. If the slope is 0, we know that the velocity is 0. And that's this piece right here of our velocity graph. It's hard to see it, so I put the rule over. Okay, so a constant function for position yields no velocity because you're constantly in the same place. You're not moving. The second one is uniform motion. Uniform motion. Uniform. Uniform means constant, but the word motion in front of it means that you're probably moving. Now, technically, uniform motion is this also. I'm uniformly moving with what velocity right now? 0. So technically, uniform could mean no velocity, but you use the word stationary. When you hear uniform motion or constant motion, it refers to something like this. Again, 1 step every second, 2 steps every second, whatever it may be. So what do I know about my position? If I'm moving with constant motion, what do I know about my position? What is my position doing? What can you say, Seb?
Well, the slope is constant, so it's the same average time.
What's the same, Seb?
This, the movement that you, the amount of time,
Yeah, I like that. The amount of meters you moved, every time period is constant. So if I take 1 step in a second, I have to take another step in a second. And in another step, because of that constant motion, Seb got ahead of himself and said, hey, the slope is also constant here. So what kind of a value is the slope? What kind of a number? And when I say what kind, I don't mean give me the value. I mean what kind. Give me some category to fall into. A whole number. I like that. It could be decimal also. We don't know. Positive. So when the slope, again, is greater than 0, our velocity is greater than 0. Okay, our velocity. Now, what was our velocity? Our velocity was a constant because I was showing you 1 step per second. Notice there's no units on the y-axis here because I'm not caring about the actual value. I'm caring about the type of motion that's existing. Okay, so the slope of this line might be like, this is 1 step right here. That's 2 steps. I'm using units of measurement that don't really exist, steps, right? We talked about, remember, the King Louis's arm or foot or whatever it was. So if I move 1 step every 1 second, then this unit of measurement right here would be 1 step per second. Now, again, I know it's units or meters here, but I'm trying to introduce you guys to the concept that any unit can be used. So if this is what we had here, we moved, again, 1 step up every 1 second. That means our velocity was 1 step per second the whole time. Replace step with meter if it helps. Replace step with meter and it's the same thing.
So even though on the second graph the slope is 0, the velocity is still greater than 0?
Well, the second graph is a velocity graph, not an acceleration graph. Yeah. So we're not a position graph there. So I'm writing velocity greater than 0. That's not the slope. Sorry. Let me just jot it down here and make it more clear. I wasn't indicating the slope. Thank you. Okay, I was only indicating the fact that the second graph is a velocity graph. And because this slope was positive, the velocity the whole way is going to be positive 1 meter per second or step per second. Okay, we didn't get into acceleration yet. We're going to cover that in the next section after the first test, so I don't want to go too far with that idea. And let's look at the third one finally. Motion with constant acceleration. I'm using the word acceleration not to make it confusing because, again, we're going to do that in the next section, but because you should also recognize, though, how position functions look. If I were accelerating, what does that physically mean? I'm getting what? Faster. So this one makes sense for sure. Does everybody agree with that? It's a velocity graph. So what must your velocity be doing? It must be increasing, getting faster. So the velocity graph makes a lot of sense, actually. The position graph is a little bit tougher to see, but the best way to see it is to imagine a tangent line at every instant on the graph. So do what I do with your pencil for a moment. Take your pencil and put a tangent line at the beginning. It would be flat. So what's my velocity in the very beginning? 0, because the slope of the tangent line is 0. Then what happens to my slope? As I move through time, what happens to my slope? It goes from 0, it gets to here, it gets to here, it gets to here. Eventually, it kind of looks like it flattens out. But what's happening in this beginning region to my slope? Physically, what's happening to my slope value? Yeah. The slope becomes greater, yes, because the line becomes steeper. And remember, the slope of the tangent line is your velocity. So in the beginning, we'll use that tangent line. Then we can use that tangent line. Then we can use that tangent line. And eventually, if we keep accelerating, this thing will continue to climb, but it may eventually flatten out, or we might get to the same slope forever, and that means we'd eventually reach terminal velocity, or a constant velocity at the end. But compare your slopes. The red is 0 slope, and that's 0 velocity, and that's in the very beginning. And the blue is a higher slope. The green is higher than that. The yellow is even higher than that. So the slope getting greater is increasing our velocity.
So if the line, at some point, kind of, did the other, went like that, then then the velocity would go down.
Yeah. So, yeah, actually, that's a great point. So if we continued this graph, right? Say we continued this graph and it did something like this. Right, like that? Then we would have exactly that. We would have a velocity that is becoming less and less as we get toward the top, because all of these successive tangent lines would have a lower slope. See that? So the tangent line gets to be a lower slope, so the velocity goes down. And then at the top, what's the velocity at the top again?
0.
It's got to be 0, because the tangent line slope is 0. And then eventually, what kind of a slope do we get in these regions I'm drawing dots in right now? Yeah. So negative velocity, because what's happening to my position? My position is decreasing. So how would that look on a graph? Well, my velocity would eventually start to decrease. It would go back to 0, and then the velocity would become negative. That's what the rest of that graph would end up looking like. And I know the way to draw these best is having the position and the velocity right above each other, so you can line up your times like you guys did in the lab. Remember all those little segments in the lab? That was that position graph with the velocity right below it. So these times might not correlate perfectly as I've drawn the length of this graph, but that's the general shape the velocity graph would take on as a result. Jack?
At what point in the velocity graph does it go negative?
It goes negative after this region on the position graph. Okay, because after that point, after that blue vertical line there, from that point, I should use a dashed line because that's not like a slope. But after that blue dashed line there, Jack, all of the tangent slopes would be negative, right? If I were to draw a tangent line at any point here, they'd all have negative slopes, which is really right here. So that's the exact same point right there, okay? So if you want to draw a dotted blue line over there also to indicate that that's where the velocity becomes negative. The graphs are not underneath each other, so it's hard to see that those dotted lines would line up. Those dotted lines would line up if they were below or above each other. I know it's not drawn perfectly to scale, that's what I'm saying. But from that blue line over, we have negative velocity. Okay, so we have two parts of the graph, where the velocity is positive and where the velocity is negative. In between that, the velocity must cross 0 velocity. That's why it crosses the axis there. All right, let's go take a look at an example. Rank the object's velocities and speeds from lowest to greatest. So this is simply asking you about your slope and the concept of velocity versus speed. So let's start with velocity. It's the easier of the two, I think. Rank the object's velocities and speeds, but velocities from lowest to highest or least to greatest. Which would have the least velocity in this case, or the lowest or least velocity in this problem? Again, we're looking at one thing and one thing alone, right? I should see almost every hand because the answer is just the slope. So look at the three slopes. Which has the least slope, or which has the lowest, or the most negative, right? All these questions I'm asking are things you should be thinking through your head, right? All these. Natalia, what are you thinking? Yeah. So for velocities, we'll go from lowest to highest. And for velocities, we've got object 3 as the lowest. Again, because the slope of object 3 is negative. The slope is negative. So its velocity is the lowest. Its velocity is the lowest. Remember, velocity is a quantity that direction matters for. So if I have negative velocity, even negative 8 velocity is lower than positive 5 velocity. It's all about where you lie on the number line. So a negative velocity is always considered the lowest. Then what object has no velocity? What object, everybody? Object 2 has no velocity. And then the highest velocity is object 1 because its slope is positive. Now I said that the velocity was the easy part of this problem. How does the speed portion differ?
The speed one is just going to be based on, it's going to be based on like sorry, it's not the direction, but it's the like steepness of the slope.
Good. So the direction doesn't matter, right? The direction doesn't matter. It has to do with the steepness. So if I have a really, really negative slope in velocity terms, that makes it a really, really low velocity. But remember, speed, we think of speed for now, is like the absolute value of our velocity if our motion is constant. So if I'm walking with negative 2 meters per second velocity, what's my speed? Just 2 meters per second. So this object has a speed equal to 0 still, because it's still a slope of 0. Whether I think a positive or negative, that slope is definitely still 0. Then out of object 3 and object 1, which of those has the lower speed? Out of object 3 and object 1, which has the lower speed? Yeah, because again, although its slope is negative, we still consider its speed to be positive. And let's say the speed here, and we can't come up with a number, we're just looking at steepness, right? But the speed would be like over this far and down that far to give us a slope. That's how we'd calculate the speed for that one. So we'd say, in this case, it would be like, let's just pick a number like 2 for now. Okay, write yourself a note that these numbers are not based on our graph. But let's say that the speed were 2. Okay, and that would mean that its velocity would have been negative 2. And then the last graph, we'd be looking at the slope by figuring out this change and this change right here. And let's say for object 1, that its speed is, say 3.5. Okay? I'm not putting units because I'm not giving units, maybe meters per second, might be miles per hour, but we're all on the same graph. So if this is meters per second, this is also meters per second. If this is miles per hour, this is also miles per hour. Okay, so for this graph, we're not concerned about units, but I want you to recognize that, again, the velocity, the negative matters. Speed, it doesn't. So let's list our answers for speed again. So for speed, the lowest speed is going to be object number 2. The middle speed will be object number 3. And the highest speed will be object number 1. Okay. So notice what happens, these two switch places. That's the key here to this problem. Okay, what was the lowest velocity earlier has now become the medium speed. What was the medium velocity earlier has now become the lowest speed. The highest velocity is still the highest speed because the slope of object 1 was the steepest. What if I introduce the fourth line like this? Take a look at the graph, please. What if I introduced the fourth line that looked really drastic like that? Let's say my fourth line looked like a ray like that. What would I... Good. I see a lot of hands up. Good. You're getting the idea. What would I say for this problem, Julia? What do you think?
That it have the highest speed.
This would definitely have the highest speed because this line is clearly... I say clearly, but it's almost clear. It's clearly obvious that it's more steep than object number 1, but in the negative direction. Okay? This, again, has a steeper line, but in the negative direction than object 1 had. How about velocity-wise? What would that cause for velocity, Juliet?
It would have the lowest velocity.
Yeah, so this line I just introduced would still have the lowest velocity, though, because it is the most negative slope. The most negative slope is the lowest velocity. When we get to speed, though, again, forget negative and positive, just look at steepness, relative steepness. All right, let's take a look at example 7. A car travels at a constant 40 miles per hour for 100 miles. It then speeds up to 75 miles per hour for the next 75 miles. So different distances and different velocities. We're all okay with this so far? Different distances, different velocities. What is the car's average speed for the 175 mile trip? So if I want average speed, last class we've already addressed 2 formulas. We started with velocity as the change in position over time. But we're not finding velocity here, we're finding speed. How did I change this formula for speed? What did I say instead?
You replace displacement with distance covered.
Good.
Distance traveled.
Distance covered, very good. Okay, we replace our delta x, which is displacement, with distance. And that's what gives me average speed. So remember, these formulas are pretty much the same, right? And luckily enough for you guys, on your first test this year, you're really only going to have these formulas. So your first test is pretty light when it comes to formulas. As we get through topics, like in the next section, which we're going to cover right after the test, we introduce 3 new formulas right there. And every section going forward, we're going to have a couple formulas here and there. And again, they're all in your formula sheet, so you don't have to memorize them, but you have to be able to understand and apply them. For now, pretty easy formulas to use. The question becomes, how do I find, or how do I figure out this answer? Well, I need the total distance. That's not hard. What's the total distance, everybody? 175, right? So because my units are all in miles and miles per hour, I don't need to adjust anything right now. Okay, I want to, again, mention that. My units are in miles for distance, and my units for speed are in miles per hour. So really, for a problem like this, I do not need to change everything to meters per second. Is that clear what I'm saying? It's when the units disagree that matters. So if my units of velocity were meters per second, but my distance was in miles, I need to convert miles to meters. So my units of velocity need to match my units of distance or displacement or time. So here I'm given miles per hour. So my time should be in what? What should my time be in? What unit? My velocity is miles per hour. My time should be in? My time. Just my time. Just hour. Yeah, very good. Just hour. No need to make it seconds. Okay? Is that clear what I'm getting at here? So I talk about base units as meters per second, but you're going to notice that if you take the subject test in physics, if you take the AP1 exam at the end of this year, you're considering it, you're going to get units that are not SI units at times. We're going to primarily work with SI units, but I want you to get used to the fact that you don't have to always change if the problem is set up this way. The question becomes, how do I get the total time elapsed? How do I get the total time elapsed? Give me the theory, not the number, but the theory behind it. How do I get it? What am I doing? Not the answer, but what am I doing?
Well, first you find out how, in the first part, how long the car was traveling for the first 100 miles based on usually miles per hour. And then you would find the second part's distance covered. Oh, sorry.
So Morrow made the point that our denominator is really the sum of two time periods. Right? Remember delta t? We said delta. What does delta mean again? Change. Final minus initial, I've emphasized. But notice here, I don't have a final time. I don't have an initial time. But I do know, as Morrow said, that there's two parts to this problem. So if it helps you, you need to draw yourself a little picture, a diagram. Like this. Well, the first distance is 100 miles. The second distance is 75 miles. We know that in the first time period, my speed was 40 miles per hour. And in the second time period, my speed was 75 miles per hour. So remember how last class I talked to you guys about givens, unknown formula, stuff like that? The given can be a diagram. In this diagram, I'm giving all the information. There's D1, there's D2, there's S1, there's S2. And notice again, I jumped right into the formula. I probably got ahead of myself by jumping right into it. I should probably list my givens, list the equation I'm using. So I at least listed the equation I was using and looking for speed, but I kind of ignored that part of it. But I need to consider that to find my times. So how am I going to find those times, T1 and T2? How am I going to figure out time 1 and time 2? What should I do here? Vin, what are you thinking? Yeah, that's fine. But for the sake of right now, I'm calling it T. Because remember, delta is really useful when somebody gives you a starting time and an ending time. Like if I say the problem started at 3 seconds and ended at 27 seconds, then delta matters because 27 minus 3. For this problem, it wasn't like we were given a starting and ending time. We're going to calculate the time for each portion of the trip. So my question is, how do I calculate said time? How do I figure it out, Jack?
So 40 miles per hour in 100 miles. So that would be about 2.5 hours.
How did you get it, Jack?
So 100 over 40.
So what formula are you really using, Jack?
Delta x divided by delta t.
Yeah, or this one right here. Same thing. Very good.
Yeah.
You're really using this formula and solve this formula for t. Think about this formula on the side, okay, as S equals d over delta t. And then solve this for delta t. This becomes delta t equals distance traveled over speed. So for the first time period, Jack noticed his units. He used his units to help him. He said, well, you know what? It's 100 miles at 40 miles per hour. So take 100 over 40, which is where 2.5 is going to play a role for the first time period. 100 miles over 40 miles per hour. My units of miles cancel. My units at the end are hours. How about the second part? I'm going to really do what? Anything different, George?
Just do the same thing except for 75 and 75.
Precisely. 75 over 75 is just 1 hour, right? So a nice, easy second part of the problem here. And again, let's show that if we'd like to. This first part was delta T1, or T1, I guess, if I'm going to be consistent. And then T2 was during the second time period. which was 75 miles or at a rate of 75 miles per hour, which means it took 1 hour. So again, these numbers are going in here and in here. So what I want you to see of this problem is that although the governing formula is S bar equals D over T, I may need to use that formula in the problem earlier on when solving it for T, when not actually calculating this average speed. So I'm not getting the average speed from using these two formulas. I'm getting the time periods taken. Then I know the total time is 3.5 hours, and I traveled 175 miles. So now I can find my average speed. What would that turn out to be? What does that come out to be for average speed for this problem? George, what do you got?
Miles an hour.
What is it?
50 miles an hour.
Exactly. Worked out? Nice. Okay, and miles over hour is the same thing as writing MPH. Okay, you use MPH, miles per hour. You'll see that as a unit on exams or on like standardized tests, MPH. If it's kilometers per hour, you usually see km/hr. They don't usually write kilometers per hour as like kph or anything like that. Okay? So, did this answer surprise you is my question. Let's talk about this for a second. This is where it's going to separate honors physics from a regular physics course. Does the answer make sense and why? Can you explain with logic and with reason? You validated the answer with math just now, or we've come up with the answer that way. But now let's argue why it makes sense. That's the real question here. Why does it make sense, Jack?
Well, we know it has to be between 40 and 75.
Good. So that's our first assumption. It's got to be between 40 and 75. Everybody agree with that? Because it can't be outside that range if you've only traveled with two separate velocities. Agreed. That's step one. I'm going to ask another help for step two.
You know it's going to be closer to 40 because you travel a longer distance with that speed.
Very good. So the velocity of 40 miles per hour, not only do you travel a longer distance, but it also takes you more time. The time is actually the key. The distance matters, but the time matters more. Let's write that down. So for example, I can do a round trip. Here, I'll give you a minute to write that down. First, the time of 2.5 hours is what matters more. You're spending more time at a lower velocity, speed. You're spending more time at a much lower speed. It's not the distance in the end. And I want to prove that to you, actually. Which is kind of tricky to think about. Again, you're spending more time at a lower speed, so your answer needs to be closer to that lower speed than the higher speed. And again, 50 is closer to 40 than it is to 75. So let's give a scenario. I want you guys to think about this, and this is an extension to this question really right now. If I were to walk across the room, watch my motion please, from eraser to eraser, this is perfect. See the erasers? Eraser to eraser. Here's my first lap. This speed the whole way, and you gotta wait for me to do this the entire way across, which is really annoying. And then, once I make it to the end, right, I go a certain distance d. Well, I go the same distance d. Well, I went, say, 2 meters in one speed, 2 meters back at a different speed. So you would sometimes assume that your average speed is the average of your two speeds. But it took me far longer to walk at this rate than it did to walk back quickly, right? So it turns out that your average speed in that scenario will not be the average of the two speeds. If this were a speed of 0.5 meters per second and this speed was 2 meters per second, you're not just going to average those two numbers, even though you walk the same distance both ways. It's the time duration that causes a weighted average. You know what I mean by a weighted average? Weighted average? Okay, the concept of a weighted average simply means that one of those laps had more significance than the other because it took more time. Okay? So this is a very good question for a conceptual question on a test. Conceptual. Notice on your quiz, how did I label your questions? Conceptual and quantitative. I'm using the word quantitative instead of mathematical, which just sounds better. But quantitative means there's numbers and equations involved, right? But the first one, it was the concept was what matters. The units that you matched up, there's no math involved in the first problem. So this would be a conceptual idea of the follow-up I just mentioned. Whereas this example itself would fall into a mathematical or quantitative case. Again, on your test, you could expect multiple choice, which could be either conceptual or quantitative. Then you'll have conceptual with words. Then you'll have quantitative with equations and math. So the same format of all tests. I want you guys to get used to the kind of questions you'll expect. Let's talk about this next idea. Instantaneous velocity. Almost done. Okay. And then stop in about 3 minutes. Instantaneous velocity. Here's the concept. Remember the tangent line we've been drawing the whole way? That's instantaneous velocity. It's the velocity at an instant, at a moment in time. There's no time duration. We are taking a look at the time duration going to 0. That's what's happening here. Maybe circle this in the equation. We're going to use this phrase limit. In pre-calculus this year, you're going to use limits. The limit simply means this. It simply means this. Ready? Draw yourself a graph. Call this position, call this time. Draw yourself a simple curve like that. Call this the starting time. And call this the ending time. Okay, call those 2 points starting and ending. If I were to connect those 2 points with a straight line, and I were to figure out the slope of this line, that'll give me the change in position, the change in time, and the slope of this line will give me the average velocity. But if I take, now watch what I'm doing. I'm going to use a pointer, so you might have to see it. If I take this point right here, and I slowly just move it back, further and further and further. Say I put the point now up over here, and I find a new slope. Well, now I'm still getting the average velocity between those 2 points. But eventually, if I take that point and move it so close to the first point, put it right up against it, please. Put it right here. Make the 2 points literally next to each other, adjacent to one another. And when I do that and connect them, what am I getting? I'm getting the slope of what kind of a line again now? What do we call this line? The tangent line. So the slope of a tangent line is actually the instantaneous velocity. It's the velocity at the instant t0 is what it is. Again, this is average velocity, those other two. But if you can get those time periods to be really close to where tf minus t0 is practically 0 and no time has elapsed, almost no time has elapsed, you're getting the velocity at that instant itself. George?
If the 2 points were directly on top of each other, would it be 0?
Well, but then can you divide by 0 in math? What do you get?
So
Undefined. So technically speaking, this is calculus actually you guys are learning right now. In calculus, we talk about the fact that it doesn't actually become 0, this little gap, but it gets infinitesimally close to 0, meaning really, really close. Like a time period of 0.00001 seconds is what your denominator becomes. And if you have a small change of position, which is what we have here, over that really small time period, and the way I can see that, George, take a look. Ready? Now we can see the time period, right? Now we can see that really it's changed some position in some time. So my position change is the vertical, my time is the horizontal. So technically there is a slope on a zoomed in scale. Okay, really good question there. Really good question. Let me see if I want to just skip ahead and see what I want to do to finish, because I do want to mention your projects. We'll look at real quick some graphs to see what I'm referring to. So first, these are velocity graphs. Write a note here. These are velocity graphs. They're not position graphs. In the first case, what could you conclude about my velocity? What could you say in the first graph? The velocity is constant. So if you were to compare the average velocity to the instantaneous velocity at any moment on the first graph, what could you say? The average velocity and the instantaneous velocity at any moment on the first graph.
They would be the same.
They would be the same. The velocity is always 40 kilometers per hour. At any instant, the whole time. So in the first case, the average velocity equals the instantaneous. In the first case, they're equal to each other. But look at the second case. In the second case, the average velocity is 30 kilometers per hour. But it is not equal to the instantaneous velocity at any moment. Remember, that this is not a position graph. So we're not looking at the slope of the tangent here. This is a velocity graph. So the velocity, follow my finger please, or follow the cursor on the screen. The velocity increases, becomes constant. The velocity decreases, and then becomes constant. And then the velocity decreases. So the velocity at any instant is simply the y value. The velocity here is 50, 50, 50, 50, 40, 30, 20, 20, 20, 20, 20, 20, 20, 10, 0. So the velocity is changing because the actual graph is changing. It is not constant. So this is a velocity graph and what you should think about with velocity graphs. The next three slides are kind of what I already indicated. Okay, this is a position time graph where the 2 points are pretty far apart. Watch what happens, please, on the next slide. If I think about a point that's even closer, like P3, the line gets different. The slope changes with the different secant lines, eventually becoming tangent. And then this is what I was kind of referring to earlier on. The velocity is positive. The velocity is more positive. At the top, the velocity is 0. And then at P5, the velocity is negative. Okay, this is kind of what we talked about earlier already. So to quickly finalize or summarize here with our graphs, in the beginning, when you see curved up, we have accelerated motion. When we see the position is gradually going up with a constant rate, we have a constant speed. When it starts to teeter off at the top, it's slowing down. And then when it actually becomes flat as a position function, it is stationary. So those are the 4 kinds of motion you could expect on a position graph. Now, those are all showing, in this case, where the position is increasing. The position could then decrease afterward. Okay, decrease afterward. I know I rushed to that last piece, but we've kind of been talking about those graphs all along. So here's your homework again, the homework that I mentioned last week that you probably wanted to start a little bit earlier, but if you didn't start it, please get to it tonight.